A Dyson sphere is a theoretical megaproject, a ginormous sphere encircling a star with platforms orbiting in tight formation. It's supposed to be an ultimate solution both for energy production and living space. The creators of a Dyson sphere get a lot of surface area for habitation and the ability to catch every tiny bit of solar radiation and heat produced by their central star. The first person to theorize about such a bizarre construction was British-American theoretical physicist Freeman Dyson. According to him, an intelligent extraterrestrial civilization could consider building this sphere after colonizing some moons and planets in their local stellar neighborhood. With the growth of their population, these aliens would need more and more energy to sustain their lives. Dyson calculated that assuming that this alien society grew at 1% per year, their area and energy needs would become 1 trillion times larger in a mere 3,000 years. And if their solar system contained a space body similar in size to Jupiter, they could take it apart and spread its mass in a spherical shell by building a structure at twice the distance between our planet and the Sun. This amount of material would be sufficient to build a huge number of orbiting platforms. Each of them could be 6 to 10 feet thick, which would basically allow this civilization to live on their star-facing surfaces. A shell this thick could be comfortably habitable and capable of holding all the equipment needed for using solar radiation without falling onto the star from the inside. But after absorbing all this solar energy, the sphere would have to re-radiate it. Otherwise, the energy would build up, eventually causing the construction to melt. It means that the light of a star wrapped in a Dyson sphere would look dimmed or even completely darkened, depending on how dense the platforms orbiting it were. At the same time, it would glow unusually bright in infrared wavelengths invisible to the unaided eye. Because of this infrared radiation, Dyson spheres are classified as a type of technosignature. It's a sign of activity that astronomers can use to discover intelligent life forms in the universe. Some Earth-based researchers have infrared maps of the night sky they examine in hopes of spotting Dyson spheres. So far, no one has ever found one. However, one study has selected several Dyson sphere candidates. Its authors have processed large amounts of information using a special data pipeline for combining and analyzing information. One of the main search criteria is the detection of excessive infrared radiation. At the same time, it's important to distinguish this radiation from that emitted by natural objects. After a complicated filtering of millions of objects, the researchers identified 7 potential Dyson spheres. Sure, further analysis is needed to determine their nature. To do this, scientists want to use optical spectroscopy, which may reveal more details about these objects and their origins. At the same time, the researchers admit that these candidate Dyson spheres might have other explanations. For example, they could be debris disks or protoplanetary disks of young stars. Only more research can show whether we can find traces of other civilizations among star systems. For now, it's still an open question. Interestingly, Dyson spheres have been spoken about a lot in science fiction. As far back as 1937, a novel called Star Maker by Olaf Stapledon described systems in one particular galaxy that were surrounded by a gauze of light traps, which focused solar energy for intelligent use. That was the reason why the entire galaxy was dimmed. In another novel, Ring World, the writer spoke about a ring-shaped artificial structure surrounding a star.
We almost know what happened right after the Big Bang. Scientists understand the universe really well from about 1/1,000,000,000th of a second after it all started. But what about before that? That's where everything gets fuzzy. First of all, we need to remember that our universe is constantly expanding. You can imagine such expansion as inflating a balloon. We know the equations that describe the expansion of the universe. These are the equations of Einstein's general relativity theory. They state that the presence of matter in the universe leads to its expansion. And just like a balloon is inflated at different speeds by hot and cold air, the speed and character of expansion of the universe depends on what type of matter dominates. Slow particles, hot relativistic matter, or even mysterious dark energy. So if you imagine his expansion as galaxies just flying away from an explosion, you need to rethink it. By the way, the Big Bang wasn't actually an explosion, so instead, space itself is expanding, pulling galaxies along with it, kind of like corks floating in a stream. This movement is what we call the cosmic flow. Space is like an elastic medium that stretches, carrying everything with it. Physicist John Archibald Wheeler found a great way of describing it. Matter tells space how to bend, and space tells matter how to move. Basically, the stuff in the universe and space itself are in constant interaction. In general, expansion is an important property of the universe from the very beginning. But how do scientists study what happened to the universe billions of years ago? We cannot look directly into the past. Fortunately, there are indirect ways. When the life of the universe began, it was almost homogeneous, and galaxies appeared from small unevenness. In other words, the distribution of galaxies in the universe shows us the unevenness of matter in the early universe. Another super useful tool is cosmic microwave background spectrum analysis. Let me explain where it came from. At first, the universe consisted of plasma, which is charged particles. Light cannot spread through such a substance because light is scattered by charged particles. It's similar to when we are running through a forest. We have to dodge trees. At some moment, positive and negative charges united, and the universe became electrically neutral. After that, light particles could easily move through it because they had nothing to scatter from. It's as if you were running across a field and not through a forest. So the radiation that was at the moment when the universe became electrically neutral reaches us without problems. It's as if we have a photograph of the early universe. This is a real treasure trove for scientists. Now, when physicists don't have enough data, they use models to make educated guesses. Because in addition to the cosmic microwave background and the distribution of galaxies, there are other indirect observations of various stages of the evolution of the universe. And those different models physicists study must pass all these numerous tests to describe the observables. Then, if we have a model that describes the evolution of the universe, we can use it to understand not only how the evolution of the universe occurs, but also to look into the past. What was its state in the earliest stages? Well, things were extreme. The universe was small, matter was squeezed, and the temperature and pressure were sky high. Go back far enough and you'll hit a point where everything is just a super hot, primordial soup of elementary particles zooming around and smashing into each other. At the time, atoms didn't even exist yet. Even more exciting, today's observations predict that even earlier, there was a stage of very, very rapid expansion. Almost instantly, the universe expanded many, many times. Such fast expansion is called inflation, and it might explain a few big mysteries that cosmologists struggle with. For example, why the geometry of the universe is so perfectly flat instead of curved. Then, there's the horizon problem. How is it that the temperature of the cosmic microwave background, the afterglow of the Big Bang, is almost exactly the same no matter where you look in the sky? And finally, it can help us understand what caused the first tiny clumps of matter, which eventually led to galaxies, stars, and planets to form. Inflation solves these problems because the rapid expansion it proposes would have smoothed everything out, explaining the universe's flatness and even temperature, while also allowing tiny quantum fluctuations to seed the first galaxies. But scientists are still working with other models and theories. So while this idea answers some questions, it doesn't give us the whole picture. There's still much we don't know. But by exploring this and other theories, we're getting closer to understanding how everything began. As we have already found out, the presence of energy in the universe leads to its expansion, and for the expansion to be so fast, a lot of energy is needed. And apparently, this energy came from some unknown field. We know that there might be new forces or particles that only show up at super high energies, but we haven't found them yet. This is where the inflaton field idea comes in. It's the most popular theory to explain the early universe. The inflaton is a field that might have caused the universe to expand incredibly fast in an event called cosmic inflation. Where could this field come from? The standard model of particle physics says there are 12 basic particles of matter, 6 quarks, and 6 leptons. The most famous are the up and down quarks, which make up protons and neutrons, and the electron. All the elements in the universe are made of just these three kinds of particles. And then we've got the Higgs boson, which gives particles their mass. The amazing thing is that this particle model explains what the universe was made of in its first trillionth of a second, after the Big Bang. But naturally, we want to go even further back, closer to the actual Big Bang moment. Unfortunately, or perhaps fortunately, we can't recreate the crazy high energies that existed at the start of the universe in any experiment. We have tested our particle physics theory. Only up to the energies that the Large Hadron Collider produces. What happens at higher energies, we can only guess. So scientists have to build their ideas based on what we know. They use the theories of quantum fields to imagine what could have happened at those extreme energy levels. It's not random guessing, though. These theories help us figure out how particles would behave at higher and higher energies. Perhaps one day, our particle physics will be supplemented with new particles that are responsible for inflation.
What occurs when a star depletes its energy reserves? Interestingly, it balloons to a magnitude many times its original dimension. This happens because, as the star's core exhausts its hydrogen supply, it begins to shrink due to its gravitational pull. Yet, hydrogen fusion still persists in its outer layers. As the core shrinks and heats up, the external layers also get warmer, leading to their expansion, enlarging the star's radius. As it expands, the star consumes everything in its path, even possibly its own orbiting planets. Although astronomers have observed stars on the brink of, or just after, consuming planets, witnessing this event in action remained elusive. However, a groundbreaking discovery by researchers from various institutions revealed a star in the act of devouring a planet. Astonishingly, this cosmic drama unfolded not in a distant galaxy, but within our very own Milky Way, a mere 12,000 light-years away. And the subscribe and like button is only a few centimeters away. Go ahead and click. Thank you. Astronomers observed an intense flare from a star, whose mass ranges between 0.8 and 1.5 times that of our Sun, located near the Aquila constellation, resembling an eagle. Its brightness skyrocketed to over 100 times its usual within just 10 days, before diminishing rapidly. Intriguingly, this initial fiery burst was succeeded by a cooler, prolonged signal. This unique sequence hints at one possibility. A nearby planet was devoured by the star. Which planet met this fiery end? Experts suggest it might have been a scorching world, weighing anywhere from 1 to 10 times that of Jupiter. Such celestial bodies are often referred to as hot Jupiters. These massive exoplanets, akin to our solar system's Jupiter, complete their orbit around their host stars in less than 10 days. This particular planet had been inching closer to the star over time until it was irresistibly drawn into the star's atmosphere and eventually into its core. This cosmic dining event took place roughly between 10,000 and 15,000 years ago, when the star had been shining for about 10 billion years. Despite its advanced age, the act of engulfing was shockingly swift, like a quick bite. This is in stark contrast to other hot Jupiters, which saw more of a gradual consumption by their stars. It's uncertain to the astronomers if this star has other planets in its orbit, possibly maintaining a safer radius. But even if such planets exist, it could be millennia before they end up on the star's menu. Regardless, with this newfound knowledge, astronomers are keen to spot more of these celestial feasts. One day, our very own planet and a chunk of our solar system will face a similar destiny. Everything familiar will vanish in the blink of an eye. But no need for immediate panic. This event is slated for about 5 billion years from now. That's the estimated timeline for the Sun to exhaust its fuel and swell immensely, consuming the inner planets, Mercury, Venus, Earth, and Mars. Should humanity have settled on another celestial body by then, they'd have front-row seats to this cosmic upheaval. The Sun's luminosity would spike dramatically, casting off matter into the cosmos, and potentially even consuming Earth in its fiery dance. This phase of the Sun's life will span about 10 million years. Once the core temperature reaches 100 million K, a helium flash will occur, initiating the thermonuclear fusion process that synthesizes carbon and oxygen from helium. With this newfound energy source, the Sun will shrink in size. After around 110 million years, when the helium reserves deplete, the Sun will undergo a tumultuous expansion of its outer layers, transforming into a red giant once again. This Sun phase will be marked by intense flare-ups, with its luminosity at times exceeding its current level by 5,200 times. This will result from previously untouched helium remnants entering the thermonuclear reaction. The Sun will remain in this state for about 20 million years. The Sun's mass is insufficient for it to end its evolution in a supernova explosion. After traversing the red giant phase, thermal pulsations will cause its outer shell to be stripped away, forming a planetary nebula. At the heart of this nebula, a white dwarf will remain, a remnant of the Sun's core. This object, incredibly hot and dense, will be comparable in size to Earth. Over countless millions and billions of years, our once radiant Sun will cool and dim. This life cycle is typical of low to mid-mass stars. When watching a beautiful sunset over the sea and in the mountains, have you ever thought about what a sunset on Mars looks like? Or on Venus? Do they have the same reddish hues as sunsets on Earth? Not really. You see, sunsets look very different on different planets because of the composition of their atmospheres. Sunlight scatters off of the molecules that make up an atmosphere. This process is more effective at shorter wavelengths, which is the blue end of the visible spectrum. That's why we perceive the sky on our home planet as blue. But at sunset, light needs to travel longer distances through the atmosphere. That's why we see yellow and red hues. Now, let's move to Mercury and check what sunsets look like there. Both sunrises and sunsets on Mercury are views to behold. The Sun seems 2.5 times larger in the sky over this planet than when you look at it from the surface of Earth. It also rises and sets twice during a Mercurian day. It rises, arcs across the sky, stops, moves back to the rising horizon, stops again, and restarts its way toward the setting horizon. Such bizarre maneuvers occur because Mercury rotates 3 times for every 2 orbits around the Sun, and its orbit is extremely elliptical. But if you expect to see a blazing sky and the hues of red, you'll be disappointed. Mercury has almost no atmosphere, so its sky is always black since light doesn't get scattered at all. Let's continue our journey and go to Venus. There, at sunset, a bright yellow fades into orange, brown, and then when the Sun disappears, black. The planet rotates on its axis very slowly, so to see a sunset, you'd have to wait almost 1/16 times as long as you would on our home planet, half of a Venusian year. Mars is widely known as the red planet because of its rusty color caused by the presence of iron oxide in its soil. But sunsets on this planet would look surprisingly blue if you watched them from the surface of Mars. Fine dust in the atmosphere of the planet scatters light and makes the blue hues around the Sun's area of the sky brighter. A Uranian sunset is azure, fading into royal blue with some hints of turquoise. The pretty colors come from the interaction of sunlight with the planet's atmosphere, which mainly consists of hydrogen, helium, and methane. These gases absorb the longer wavelength red portion of the light, and the shorter wavelength blue and green light gets scattered when photons bounce off the gas molecules and other particles in the atmosphere. In 2014, scientists working with data received by NASA's Cassini mission showed what a sunset on Titan could look like. The largest moon of Saturn is surrounded by haze and smog. It's the only satellite in the solar system with a measurable atmosphere, which mostly consists of nitrogen, around 95%, and methane, about 5%. High in the atmosphere of this moon, the nitrogen and methane get split apart by the ultraviolet light from the sun and high-energy particles accelerated by Saturn's magnetic field. The compounds produced during this process create a thick, orange-colored smog. As the sun sinks toward the horizon, these orange hues turn into a deep brown. Now look at this. It looks like a sunset on Earth, right? But it might actually be what it looks like on Saturn. We have to say might because, just like all images from space, we can rarely get the color right. They are neither true nor false. They just represent the physical processes underlying the subjects of the images. As for the photo of a sunset on Saturn, it's hard to say if it looks exactly like this before we get more scientific data.
NASA sent a spacecraft right into the sun. It's the fastest human-made object ever, and could cover the distance from Philadelphia to Washington, D.C. in just 1 second. The Parker Solar Probe's mission is to study our star's dangerous behavior. Scientists warn that massive solar storms are inevitable, and the consequences could be catastrophic for our planet. The spacecraft got 7 times closer to the sun than any other probe ever did. It managed to do so during its 20-second flyby to the star since its launch in 2018. Because our star is so massive, its gravity is really strong, like a giant magnet. As the probe flies around the sun, it uses gravity to go faster and faster and eventually picks up that crazy speed. As it got closer and closer to the sun's corona, which is its outer atmosphere, the probe had to survive temperatures of 2,552 degrees Fahrenheit. That's hot enough to melt many metals. It was protected from that heat and radiation by a 4.5-inch thick carbon shield. It kept the tools inside the probe safe and running at around room temperature. The scientists went to all this effort because they're hoping to solve a big mystery about the sun that's been puzzling them for ages. The surface of our main star is already super hot, but as you move closer out to the corona, the temperature shoots up to millions of degrees. And it doesn't make any sense because it's farther away from the sun. So maybe we could finally get some answers about this heat phenomenon. The mission is also going to help us understand something called solar wind. The sun is constantly shooting out tiny bits of energy and charged particles into space, like a never-ending breeze of electricity. When this solar wind hits Earth, it can create amazing light shows in the sky called auroras. The more active the sun is, the farther south you can see auroras. Our star follows natural cycles that last about 11 years. The activity goes from low to high and back down to low. Right now, we're in the solar maximum, the peak of the activity cycle. That's why we've spotted beautiful auroras in the most unexpected places in 2024. The downside to it is that the sun's activity can send out bursts of energy and charged particles that can mess up things like radios, satellites, and even GPS. It can be dangerous, especially for astronauts out in space who aren't as protected as we are here on Earth. Humans wouldn't feel the compression of the planet's electromagnetic field because of all the extra radiation, but power grids are really sensitive to it. If we don't act fast, when it happens, the influx of energy will go into power transformers all over the world, disrupt them, and leave big areas without electricity. If this happens during a hurricane or a tornado, when communication is already super important, it could make it much harder for emergency services to communicate and save lives. That's why it's so important to learn to predict this space weather. It's tricky because, unlike most disasters, like earthquakes, floods, and volcanoes, it doesn't leave behind any kind of physical evidence. The only big solar storms we really know about happened in 1859 and 1921. The first one, called the Carrington event, was so wild that it made sparks fly from telegraph wires. The auroras were seen all the way near the equator. Scientists back then were using a special kind of paper that reacted to light to record solar activity. During the Carrington event, the reading from the sun went off the page, literally. Whatever was happening, it was so extreme that we still don't fully understand it. Then, there was the New York Railroad Storm of 1921. It was powerful enough to knock out telegraph systems across the US, Europe, and the Southern Hemisphere. The storm boosted radio transmissions for a bit, making them travel farther than usual. But back then, there weren't nearly as many radios, so it wasn't super helpful. The bigger problem was the electrical grid in the US, which was heavily damaged. Back in 1859 and 1921, people weren't as dependent on tech as we are now. If a storm like that hits today, the consequences could be way more catastrophic. Scientists from New Zealand who study space weather are working on simulations trying to prevent disasters from happening. They say one of the possible options to do it is to study other suns like ours elsewhere in space. If we get data from thousands of stars, not just one, the picture for analysis would be more complete. So far, scientists have launched or plan to launch several other missions in addition to the Parker Solar Probe. Meanwhile, NASA is working on another mission, launching Endurance, robotic moon machinery on steroids. Its main mission will be to collect samples from key lunar locations that will later be retrieved by astronauts from the Artemis program. These samples are spread across the largest impact basin on the moon, separated by hundreds of miles. To do it, Endurance will have to be way more advanced than Perseverance, NASA's current most cutting-edge rover. Endurance will drive roughly 100 times further, drive 10 times faster, and collect roughly 200 times more sample mass. Endurance would also be the first planetary rover to drive at night. And because it will be on the far side of the moon with limited communication to Earth and surface data, it will have to drive autonomously between sample locks and make its own decisions in tough conditions. When it reaches its destination, it's going to switch to a more classic way of doing things. Scientists back on Earth will get involved directly, guiding the rover to explore the sites and collect samples. The teams on Earth will also keep an eye on how the rover is doing by monitoring its telemetry, which is the data it sends back, like its health stats. If they spot any signs that a part is wearing out or something isn't working quite right, they'll tweak the plan to keep things running smoothly. All this will cost huge amounts of money, probably way more than the Viper moon mission that was cancelled after NASA had spent around $450 million on it. While Endurance is in the planning stage, the Blue Ghost lunar lander is already on its way to the moon. Its main mission is research. It will spend 25 days in Earth's orbit, taking measurements and waiting for the right time to fling itself to the moon. After 4 days in transit, Blue Ghost will hang out in lunar orbit for another 16 days to collect more data. Then it will descend to one of the largest basins on the moon and spend 1 lunar day there. It will measure subsurface thermal data, radiation levels, and other important data. At the end of its mission, Blue Ghost will take some final pictures of the lunar sunset. It isn't designed to return back to our planet, so when the night falls, it will do some final work and go offline for good. NASA chose the team of University of Florida aerospace engineers to work on another innovative space project. It will cost $12 million, and its goal will be to improve the way we track changes in tectonic plates and oceans on Earth from space. It will use state-of-the-art sensors that will measure even the tiniest gravitational changes. The data it gets will help scientists monitor droughts, assess groundwater reserves, and better understand changes in sea levels. They expect to launch it around 2027 aboard a SpaceX Falcon 9 rocket.
What if the sun went boom? Well, you can guess it would be super bad news for us. This was sure a short video, huh? Nah, wait, I have more. If the sun blew up, chaos would ensue in our solar system. But scientists tell us that it will certainly happen one day. But why? How exactly would events unfold? And is it possible for us to somehow survive this event? Hey, let's delve into it. First of all, get ready for a journey to the sun's core. The sun's heart is packed with hydrogen atoms, having an out-of-this-world dance party. These atoms are so excited that they smash into each other with all their might. And when they collide, something magical happens. It's called nuclear fusion. And in this fusion fiesta, the hydrogen atoms combine to form helium atoms, a chemistry experiment on a grand scale. During this nuclear fusion, a teeny bit of mass from the hydrogen atoms is transformed into a massive amount of energy. It's Einstein's famous equation E=mc² coming into play. Energy is unleashed in the form of light and heat, radiating outwards to brighten up the entire solar system. And once all these processes get going, a bunch of energized particles called photons join the fun. These photons are like tiny packets of light, bouncing and zipping around in all directions. They play a crucial role in carrying the sun's energy through space, illuminating our world and warming our cozy planet. But to keep all this going, so that atoms don't escape and create complete chaos, the sun's core needs to be under tremendous pressure. This pressure comes from the immense weight of the sun's outer layers pressing down on the core. The outer layers are squeezing the inner core. But the inner layers don't give up. The energy created from fusion and the bustling photon party tries really hard to escape the sun's core. But the core is so dense, like me, and the pressure is so big that the energy takes its sweet time to make its way out. It bounces around, gets absorbed, and re-emitted by other particles. Eventually, after a long time, it reaches the sun's surface and zooms off into space, reaching us as sunlight. So now you know how the sun works. Now, what happens once it reaches the end of its life? Well, here's the twist. Our sun has a limited supply of hydrogen fuel. In about 5 billion years, it'll run out of its fuel. After that, the star will undergo some big changes. Now, pay attention, because there's a pretty good chance we're all going to miss this. First, the sun will puff up and become a red giant, exploding like a balloon. It will grow so big that it will swallow up the inner planets, including our beloved Earth. Talk about a sun taking up all the space. So we won't even see the end of our sun unless we move somewhere further away. After the red giant phase, the sun will shrink a bit. Its outer layers will fade away into space, leaving behind a beautiful planetary nebula. It'll be revealing its glowing core. Ooh! The core, now filled with helium,
will start sounding weird.
And will start fusing heavier elements like oxygen and carbon. These reactions won't be as energetic, like a party with less dancing and more chill vibes. Eventually, even the helium will be used up, and the sun will become a compact white dwarf, a stellar retiree enjoying its retirement home. Scientists estimate that the sun has about 7 to 8 billion years left before it dims its lights. Don't worry though, by that time, humanity might have traveled to far-off galaxies, or maybe even evolved into amazing space beings. So our sun won't go out with a bang like fireworks. It's not big enough to become a supernova or a black hole. Those stellar superstars need way more mass than our sun to pull off those cosmic tricks. But what if it blew up very suddenly, just like an abrupt event without any reason? Well, let's see. Imagine this. The sun goes boom, and Earth is in for a wild ride. The event unleashes an insane amount of energy, sending a shockwave racing through space at the speed of light. It takes about 8 minutes for this shockwave to reach Earth. Why? Well, the sun is a whopping 93 million miles away from us on average. So it takes a little over 8 minutes and 20 seconds for the sun's light to travel all that distance and reach us. But let's talk about the event itself. It would be a great sight to witness, but sadly, it would also be the end. Roll credits. The crazy amounts of unleashed energy would cause the sun to expand rapidly, again swallowing up the inner planets, including our Earth. And that's not all. Brace yourself for a massive burst of radiation. The sun would unleash a torrent of supercharged particles. We're talking about X-rays and gamma rays, the kind that can seriously mess things up. When these high-energy particles hit the atmosphere, they go wild, causing all sorts of chaos. They ionize the atmosphere, creating a ginormous electromagnetic pulse. This pulse is like a shockwave for electronic devices. It fries them, zaps them, and leaves them useless. So if your gadgets aren't protected, they're in for a rough time. Speaking of rough times, after that, it's instant vaporization for our planet. But the sun's grand finale just doesn't mess with Earth. It wreaks havoc on the entire solar system. That massive burst of energy would be crashing into everything in its path. Planets and other objects get knocked off of their cozy orbits, causing chaos and unpredictability. The asteroid belt between Mars and Jupiter, kapow! It's gone, obliterated, or scattered to the cosmic winds. And even planets that will survive this event will probably go off their orbits to wander somewhere. And let's not forget about the outer planets, like Jupiter and Saturn. These giants generate their own internal heat, which keeps them cozy and attracts lots of moons. But the sun's boom would steal their warmth, turning them into incredibly cold places. And now that we've discussed how catastrophic all this would be for everything in our solar system, let's ask the logical question: can humanity make it? The short answer is nope, we wouldn't make it. Everything would be wiped out, except maybe some sneaky bacteria hiding in the shadows. But in a crazy scenario where the sun gave us a heads up about its plans, we might have a fighting chance. If we knew in advance and had time to prepare, we could get our survival gears turning. So what could we do? Since Earth itself won't survive the sun's tantrum, we'd have to move somewhere. Remember how we mentioned that not all planets would be completely destroyed? Well, sadly, the ones closest to the sun, Mercury, Venus, and Earth, would disappear. So the easiest option would be to move to some other solar system with its own Earth-like planet. But what if the Earth somehow managed to survive this catastrophe? Let's not think about how it happened and just discuss the consequences. Well, our climate would go crazy. During the first moments of the sun's kaboom, the radiation and particles would crank up the temperature big time, like a never-ending heat wave. We're talking major greenhouse effect. The oceans would evaporate, creating thick, fluffy clouds that trap heat and refuse to let it escape into space. And after that, without the sun's warm embrace, the Earth would quickly become an icy freezer. So we'd have to think outside the box. One idea would be to take shelter deep underground, where we won't be that much affected by radiation and sudden temperature changes. As you dig deeper, the temperature rises. So, with the right tools and resources, humanity could hunker down in fortified bunkers, surviving for a couple of years without the sun's rays. Why just a couple of years? Well, remember how we said the sun is a gravity center of our solar system? Without it, Earth would be adrift in search of a new center of gravity. Imagine our planet, our trusty satellite, the Moon, and all the other planets slowly floating away into space. Luckily, our trusty sun is hanging in there, keeping us warm and shining for many more cosmic adventures to come. So, we're safe for a few billion years. But it's always fun to imagine impossible scenarios. So stay tuned for more what-ifs.
A recent study has involved almost 200 huge stars that are reaching the end of their lives. It has given scientists more precise information about how the sun will one day end. It turns out that the sun will be about 200 to 300 times bigger than it is now by the time its game is over. For starters, let's begin with some basic information about star sizes. Giant ones reach this stage because they've run out of nuclear fuel and are no longer burning hydrogen in their core. Eventually, the core gets hot enough to trigger the next stage of fusion, which is helium burning. All the stars that were surveyed in this new study were either in this hydrogen shell burning or helium core burning phase. Even though giant and supergiant stars only make up less than 5% of all stars, or at least that we know of, they're actually really visible from a distance because they're so bright. In fact, according to scientists, about a third of all the stars you can see outside on a dark, moonless night are giant or supergiant stars. This study will eventually give astronomers really useful info about massive stars. They'll be able to figure out their size and temperature, no matter where they are or their evolutionary stage. This means they can see a star's true color and use that to find out its radius. Pretty cool, right? It does raise the question, what will our sun be like when it gets old and grumpy? To put it simply, It will expand when it starts burning its hydrogen shell, but then shrink a bit during its helium core burning phase. After a few 100 million years, it'll end up as a giant star, about 200 to 300 times its current size. Eventually, the sun will expand so much that it will simply evaporate. So, what will happen after the sun fades away? Scientists actually have some predictions about what will go down, even though we won't be around to see it. They're pretty sure the sun will turn into a planetary nebula. These planetary nebulae are chunks of gas and dust in space that come from a star that is fading away. They got their name because they looked like planets to people using telescopes back in the 18th century, even though we now know they have nothing to do with actual planets. And here's the crazy thing. Astronomers have found out they can use the level of brightness of these planetary nebulae to calculate their distance from us. In 2018, scientists also found out that the sun is the smallest a star can be to still be able to produce a visible nebula. Any smaller and it would not be visible. Stars that are up to 3 times more massive than the sun will produce brighter nebulae. The sun is currently 4.6 billion years old, but it's estimated to have another 10 billion years until its end. The sun is also getting brighter with each year. It doesn't seem like a lot now, but it's actually going to cause some big problems for Earth. In about 1 billion years, the sun will be too bright for life on Earth to survive. Our oceans will evaporate, and it will be too hot for water to form again. So unless we find a way to escape from this planet, humanity only has about 1 billion years left. Will Earth still be around by the time the sun turns to dust? It's hard to know for sure the exact timeline. But even before that happens, Earth will most likely be scorched and lifeless, with no atmosphere or oceans left. It's not clear how close the sun's outer layers will get to Earth, but if they get too close, it could cause Earth to spiral into the sun and disappear altogether. Even if our planet does somehow manage to survive the sun's giant phase, it will be orbiting a hot white dwarf, or a star that has run out of its fuel. In that distant future, the sun will be barely larger than our planet. Eventually, the sun will cool and dim completely. It'll move to another stage called a black dwarf. It will cause Earth's orbit to loosen up, and our planet will spiral into the faded sun. But interestingly, the sun doesn't get the final say in what happens to Earth. Gravity keeps planets in orbit, but it also attracts them to each other, which can cause their orbits to flex and drift. This could lead to the solar system destabilizing and ejecting planets, including Earth. Basically, a lot might happen in the next 5 billion years before the sun becomes a red giant. There's also another scenario. While most stars stay far away from our solar system, there's a chance that one could come closer in the next billion years. Even a small star or black hole could mess up the orbit of our planet if it gets too close. But don't worry too much, the odds of that happening are low because of the amount of space between stars. Our sun is a solitary star, so there's little to no chance we'll be able to catch a ride with another one nearby. However, many stars in our universe have companions. Among these stars is Castor, a stunning system that comprises 6 stars, and is one of the brightest objects in the night sky. Although humans have been admiring Castor for ages, they were not aware of its true nature until the invention of telescopes and spectroscopes. Even with the help of a small telescope, it's evident that Castor is composed of 2 primary stars, Castor A and Ba, that revolve around each other. These stars are larger than the sun and need 467 years to complete one orbit. In total, Castor is composed of 6 different stars. The biggest one, called Castor AA, is roughly 2 times larger than the sun, while the smallest has about 0.5 of the sun's mass. If humans want to survive the next billions of years, we might need to set up camp somewhere else in the universe. It may seem like something out of a sci-fi movie, but it could be our reality one day. Thankfully, NASA is already looking at some options. They've discovered 2 new planets, TOI 700e and TOI 700d. That might be new hotspots for us humans. TOI 700e is the optimistic zone, which means it could have water and even an atmosphere. TOI 700d is in the conservative habitable zone. So, scientists aren't too sure about it yet, but hey, we'll take what we can get. But hold on, before you start packing your bags, there's a little problem. How do we get there? It took John Glenn months of preparation just to circle Earth 3 times. So we might need to start working on our astronaut training. Well, at least we have some options for our future intergalactic vacation plans. Wouldn't it be nice if we could time travel so we could see what our solar system will look like in billions of years? An American physicist named Ron Mallett has proposed one interesting theory for time travel. It uses light, a resource that is abundant in the universe. His idea involves using a rotating cylinder of light, which could transport an object in both space and time, similar to how a bubble moves in a swirling liquid. Mallett suggests that a cylinder of the right shape could allow for travel to the past and the future. To test his theory, he has been trying to secure funding for an experiment. However, some scientists consider Mallett's theory to be impossible and unnecessary to test. We might also be able to travel through time if we move fast enough. According to Einstein, the way we experience time can change depending on how fast we're moving. If we go really fast, time slows down. For example, astronauts in space age a tiny bit more slowly than people on Earth. This is important for things like GPS, which would be incorrect without special adjustments because of how time is affected.
We're flying past the planets of our solar system. We pass by Mars, Jupiter, Saturn, Uranus, and Neptune. Then we move through dark space beyond the edge of our world. We've reached our destination. It's the Oort cloud. It's a hypothetical region around the solar system that holds tons of asteroids and blocks of ice. It's likely to be where the largest comet in human history was born. And now, it's heading toward the sun. Bernardinelli Bernstein was discovered totally by accident during the Dark Energy Survey. Our telescopes were pointed at distant space. Their main goal was to learn more about how the universe was expanding. Astronomers also wanted to make a more detailed map of the observable universe. Scientists analyzed over 80,000 images and found a moving object. It was alarmingly close to our home planet. Its size was an impressive 62 miles. That's about the width of Lake Michigan. It was an already active comet with a long tail. Usually, comets get a tail when they come close to the sun. The heat from the star warms the comet's surface, and light materials, like ice, begin to evaporate. This forms a cloud of steam and dust that stretches far beyond the comet. But Bernardinelli Bernstein is too far away from the sun to start heating up. This means that its surface has a different composition. It might be solid carbon monoxide. This increases the luminosity of the comet. That's why it can be observed with telescopes on Earth. We can compare Bernardinelli Bernstein to the largest meteorite to ever fall on Earth. About 66 million years ago, our planet was hit by a meteorite about 6 miles wide. At that time, the blast wave from the collision went around Earth several times. Tsunami waves caused by the impact were taller than the largest skyscrapers, and the energy from the explosion set huge areas on fire. Almost all living creatures, including dinosaurs and ancient fish, ceased to exist. The meteorite left a crater 3 times the size of Manhattan. The place where it fell was rich in sulfur. This substance evaporated because of the abnormal heat and gathered into massive clouds. This caused acid rains that were falling on Earth for several more weeks. Our newly discovered comet is 10 times bigger. If it were flying toward Earth, you'd see it with the unaided eye long before the impact. It looked like a moving star in the night sky. A few days before the comet reached our planet, you'd see it even during the day. You'd be able to distinguish its long tail, too. When the comet entered the atmosphere, it produced a booming sound so loud you'd hear it on the other side of Earth. At this point, the comet would begin to heat up because of friction with the air. It'd start burning. Countless pieces of debris would break away from the main body of the meteorite and fall to Earth. As soon as Bernardinelli Bernstein touched the surface of the planet, we'd see a flash so bright it'd outshine the sun. In a fraction of a second, a colossal amount of energy would be converted into heat. This would create the most powerful explosion in the history of our planet. It'd literally rip out chunks of ground and throw them into the air. The blast wave would incinerate everything within a few hundred miles. It continued to spread in different directions, breaking and bending trees. At one point, it reached snow-capped mountains and trigger huge avalanches that would cover many villages. The blast wave would go around the planet, shattering glass and buildings on all continents. Tsunami waves would be so high they would cover entire coastal cities. The most powerful earthquake in history would break the ground and create deep cracks. After the impact, billions of tons of dust and ash would rise into the air. A giant black cloud would completely block the sun's rays. Earth would be plunged into darkness. All the debris in the air would start melting. They'd turn into liquid lava and fall back to the surface, causing even more damage. The ash and dust in the air would cover the sun for several more months. During this time, the temperature on Earth would drop by several degrees. Even if they were hiding in deep shelters and bunkers, people, as well as all other living organisms on the planet, would be unlikely to survive this event. Fortunately, Bernardinelli Bernstein isn't going to approach Earth. Right now, the comet is about 20 astronomical units away from the Sun. That's 20 times the distance from Earth to the Sun. It means the comet will soon cross the orbit of Uranus. In 2031, it'll be 11 astronomical units away from our star. That's just outside Saturn's orbit. This is going to be the closest Bernardinelli Bernstein will approach the Sun. Then it will begin its flight back to the edge of the solar system. But the comet is bound to return again. It'll move away from the Sun and slow down until the star's gravity pulls it back. Then the comet will make another circle around our solar system. But that will take about 3 million years. Right now, we have other meteorites to worry about. For example, 3200 Phaethon. It crosses the orbits of Mars, Earth, Venus, and Mercury. Then it goes around the Sun and comes back. This cycle takes about 523 days. Then it starts over again. This meteorite is considered potentially hazardous because it crosses Earth's orbit at 7.5 Earth-Moon distances. During one of its last approaches to Earth, this 3.6-mile wide block of rock showered our planet with small meteors. Since the asteroid often passes by the Sun, its surface is most likely to look like the dry bottom of a mud swamp. It's covered in scales and cracks. As it flies past Earth, these scales break off and cause meteor showers. But the largest, potentially hazardous asteroid is the 1999 JM8. It's about the size of 77 soccer fields. It passes by Earth at 9 lunar distances. Its closest approach to our planet will happen in August 2137. If such a meteorite were to hit Earth, an entire continent could be wiped out. The rest of the world would experience massive tsunamis, but would survive the event. So naturally, scientists are thinking of ways to protect the planet from such a disaster. The first solution is a controlled Big Bang. One of the laws of physics says that if you apply some force in one direction, it'll cause a reaction in the opposite direction. So if we spot an asteroid that is about to collide with Earth, we'll need to send a rocket toward it. This way, we'll produce a controlled explosion, not inside, but right above its surface. The blast will be directed upward, and the asteroid will shift downward. Even this tiny shift would be enough to change the trajectory of the asteroid, and then it'll fly past Earth. Another way is to send a heavy object, like a spaceship, toward the space body. Every heavy object has its own gravity, so the spacecraft will have to fly close to the asteroid, which will attract the ship to its surface, but the engines of the spacecraft will resist. The ship will start pulling the asteroid in the opposite direction. This will change the trajectory of the asteroid, and our planet will remain intact. We can also ram the asteroid with the spaceship. Bam! Or we could build a space station like the ISS. It would be equipped with a bunch of huge magnifying lenses. We would send the station closer to the sun and start looking for potentially hazardous asteroids. Then, we'd point all the lenses so that the sun's rays would focus on the giant rock. The heat would begin to vaporize the matter from the asteroid's surface. That's where physics would come into play again. The matter would evaporate upward, and the asteroid would move downward. We could also wrap the asteroid in a reflective film, something like foil. Usually, space bodies absorb most of the sun's rays, but if the asteroid was covered in foil, the rays would bounce off its surface. This would create a weak pushing force. That should be enough to avoid the collision. Of course, we could attach rocket engines to the asteroid. This way, we would be able to not only change its trajectory, but also control it. But that would depend on the size of the asteroid and the number of engines. And then, we could use this massive rock to ram it into other, larger asteroids.
What the? Look! Do you see this? Part of the sun has broken off, and it's now churning above the star's surface, having formed a giant vortex. What's going on there? Well, let's admit it. We still know very little about the sun, however crucial this star is for our well-being. But in the case of the broken sun, scientists can probably explain what happened. Some of the star's plasma likely erupted from the sun's surface and broke away, creating something resembling a crown-like vortex over the solar North Pole. And still, this is just a theory. Astronomers need to conduct further analysis to figure out if this is what really happened. At the moment, they're a bit baffled, since this phenomenon is nothing like anything they've seen before. But the footage we've got is undeniably impressive. What is more alarming, though, is that the behavior of our star is currently changing. The sun is ramping up its activity. It's getting rowdier with flares and sunspots. This year, it's flared every day so far. It's also thrown up a few X-class and M-class flares in January of 2023. These flares are the largest and second largest eruptions our star can produce. Even though it sounds kind of alarming, don't worry. The sun has certain activity cycles that repeat every 11 years or so. Some of them are relatively calm, while others are absolutely wild. These cycles happen simultaneously with the fluctuations in the sun's magnetic field. When it gets the weakest at the star's poles, they switch places. This makes the polarity of the magnetic field reverse. This is the very period of time when the sun is the most active. It's known as solar maximum. Right now, we're near this solar maximum. Scientists can figure it out by analyzing unusual solar activity. But since the sun is still pretty much a mystery to us, no one can determine when the polarity reversal is likely to occur. A rough estimation is July of 2025. At the same time, we can't say that the current solar situation is normal. It's true that each sun's cycle is different from others. Some are weaker and some are more powerful. So this one, which started in December of 2019, has already significantly exceeded all scientists' expectations and keeps doing so. Which brings us back to the vortex observed on February 2nd, 2023 that impressed astronomers so much. It started as a solar prominence. This is a bright plasma filament extending away from the surface of the sun. And, let me tell you, solar prominences are an absolutely regular phenomenon. And like the most recent one, they often occur at high altitudes around the sun's crown, which is the outermost layer of the star's atmosphere, also known as the corona. Anyway, prominences like the one in question are called hedgerow prominences because they look like a hedge. But what surprised astronomers happened a bit later. The material of the filament apparently broke away and started circling the pole near where it occurred at 60 degrees latitude and at a speed of about 60 miles per second. And it lasted for about 8 hours. One scientist, who has been observing the sun's cycles for decades, claims that he has never seen vortices like that. Unfortunately, solar poles are very difficult to observe. so it might be a while till we get our answers. For the first time, a spacecraft touched the surface of the Sun in 2021. It was NASA's Parker Solar Probe that flew through our star's upper atmosphere. It also took some samples of particles and examined magnetic fields there. It was a real milestone and a giant leap for solar science. Getting their hands on the very stuff the Sun is made of will allow researchers to uncover crucial information about our star and its influence on us and the entire solar system. The Parker Solar Probe moved closer to the Sun's surface and started making discoveries that other spacecraft were too far away to see. For example, the probe examined the solar wind from within. It's a flow of particles coming from the Sun. These particles can influence us here on Earth. Even before coming super close to the star, the Parker probe found out that near the Sun, there were loads of magnetic zigzag structures in the solar wind called switchbacks. But at that time, scientists couldn't figure out how they formed and where they appeared. But now, more than 2 years later, we know for sure that switchbacks originate at the solar surface. As you know, the Sun doesn't have any solid surface, unlike our planet, but it has a superheated atmosphere, which is made of solar material bound by magnetic forces and gravity. When pressure and rising heat push that material away from the star, it eventually reaches a point where the Sun's magnetic field and its gravity can't contain it anymore. This point has its own name, the Alphane Critical Surface. It marks the edge of the solar atmosphere, and that's also where the solar wind begins. The material that manages to make it past the boundary turns into the solar wind. It drags the Sun's magnetic field toward Earth and beyond. But the most important thing is that past the boundary, this wind starts moving so fast that its waves can't return back to the Sun, which literally means severing all connections with the star. During its flyby, the Parker probe passed inside and out of the Sun's corona several times, which proved that the Alphane Critical Surface wasn't shaped like a smooth sphere. It has valleys and spikes, and its surface is kinda wrinkled. At one point, the probe even came across a pseudo-streamer. These are massive structures in the Sun's corona that rise high above the surface of the star. You can see them from Earth during solar eclipses. And you know what? For the Parker probe, passing through the pseudo-streamer was like flying into the eye of a storm. Inside, everything was much quieter. Particles moved more slowly, and there were fewer switchbacks. It was a huge change from the barrage of particles the probe encountered inside the solar wind. Now, speaking of solar flares, those are pretty dangerous for Earth. The radiation they release can interfere with our radio communication. Such storms affect all electronic systems, from the internet to power grids, and can even destroy satellites. Most solar flares last for minutes, but some continue for hours. Scientists classify solar flares depending on how brightly they shine in X-rays. You aren't likely to notice the tiniest flares if you don't have special equipment. Medium solar flares lead to fleeting radio blackouts at the poles, but nothing too serious. It's X-class flares that people should be worried about. They cause the strongest and longest-lasting solar storms. A super strong solar storm heading toward Earth won't happen at once. First, there will be high-energy sunlight, mostly ultraviolet rays and X-rays. They will ionize our planet's upper atmosphere and mess up radio communication. After that, a radiation storm will hit Earth. And finally, a colossal cloud of charged solar particles will reach our atmosphere. The particles will interact with the planet's magnetic field and wreak havoc all over the world. If an intense solar storm happened these days, it would start by disrupting GPS and knocking out satellites. If any astronauts were spacewalking at that moment, they would have mere minutes after the first flash of light to find shelter. Their spacecraft would likely be properly shielded and safe enough. The main challenge would be to get inside in time. After that, the storm will proceed to interfere with satellite communications. That's why tons of your daily activities, from calling your friends to paying with your credit card, would be at risk. But one of the worst consequences would be connected with power grids. Power surges caused by the particles coming from the sun would damage giant transformers. A powerful solar storm could cost people $1 trillion to $2 trillion. Luckily, if such a powerful solar storm was heading our way, we'd most likely get some kind of warning. Modern equipment all over the world and in space doesn't stop watching the sun even for a second. It would give us some time to prepare, between several hours and a couple of days. And if transformers were taken offline in time, the consequences wouldn't be so dramatic.
Attention! Attention! Emergency alert! This is not a drill. The Milky Way is on fire! I repeat, the Milky Way is on fire! Evacuation protocols activated. All terrestrial life forms are to be moved to the Andromeda Galaxy immediately. I repeat! Wait, a fire in our home galaxy? It all comes down to the incredibly hot gas surrounding the Milky Way. This isn't just intensely hot, it's also existed for billions of years. But what's heating this gas and keeping it that way? The Milky Way holds far more gas than stars, and this gas is crucial for forming new stars. Over billions of years, this massive reservoir has allowed the galaxy to keep producing stars. But this gas is incredibly thin and spread out, which makes it next to impossible to observe it directly. For a long time, this made it difficult to figure out how much gas the Milky Way really contains. But in recent decades, researchers finally confirmed that the galaxy is indeed surrounded by an enormous sphere of hot gas. This gas cloud extends as far as 700,000 light-years from the galaxy's center and reaches temperatures of several million degrees. At first, scientists thought the gas's insane temperature was due to the Milky Way's gravity. They believed that gravity caused the gas to swirl around, keeping it from falling inward and heating it up in the process. But then, recently, scientists have discovered something even more surprising: a second layer of gas. And it's even hotter. How did we discover this gas with a temperature of around 18 million degrees Fahrenheit? Faint X-rays coming from all directions in the sky revealed the presence of this gas. The gas also showed up as it absorbed light from distant quasars, bright objects far outside of our galaxy. No wonder scientists began looking for the sources of heat that could explain this bizarre phenomenon. They soon found that the two types of gas, the X-ray emitting gas and the absorbing gas, came from different regions in the galaxy. The X-ray emitting gas is apparently produced by a puffed-up region around the Milky Way's stellar disk. This region is a direct result of the galaxy's star formation, which is still going on. Massive stars in these regions eventually explode as supernovae, releasing huge amounts of energy. This energy heats the surrounding gas to extreme temperatures. The gas heated by supernovae becomes turbulent, moving around chaotically. Some of it escapes into the space around the galaxy, while some of it cools down and falls back toward the disk. This continuous cycle of heating, cooling, and movement keeps the hot gas layer visible in X-rays. The absorbing gas is enriched with elements like sulfur, magnesium, and neon. These elements are created inside massive stars through nuclear reactions and escape into space during supernovae explosions. Runaway stars that are flung out of the Milky Way's disk also contribute to this process. When they explode as supernovae, they create pockets of enriched gas above the galaxy's disk. The X-ray emitting gas forms a glowing layer around the Milky Way's disk. This layer never disappears due to the star formation and supernova activity happening in the galaxy. Together, these processes explain both the absorbing and emitting signals observed by astronomers. Star formation, supernova explosions, and gas movement all work together to shape the Milky Way. The hot gas not only helps regulate star formation, but also redistributes materials created inside stars. And elements produced in stellar cores are spread throughout the galaxy by supernovae, becoming the building blocks for future generations of stars. The research team plans to keep observing the gas at other wavelengths of light. This might give us even more information about how the gas behaves and what it's made of. And once we understand the dynamics of this gas, we're likely to learn more about how galaxies like the Milky Way evolve over time. We need all the data we can collect after all. We don't even know the true shape of our galaxy yet. Recent discoveries have revealed that the Milky Way is not a flat disk as previously thought. No, it has a warped structure. And the craziest thing? Dark matter might be the cause of this deformation. The first confirmation that the Milky Way isn't a perfectly flat disk came from observations by the Gaia spacecraft. Gaia mapped the positions and movements of over 1 billion stars, and its observations showed that the Milky Way extends farther outward than initially believed. At its edges, the galactic disk was a wavy, warped structure with serious deformations along the outer edge. But what causes the warp? These deformations may result from ancient galactic collisions, like the Milky Way's collision with the Sagittarius dwarf galaxy around 6 billion years ago. However, a new study suggests another possibility. The warp might be caused by a tilted dark matter halo surrounding our galaxy. Dark matter halos are invisible, yet massive structures surrounding most galaxies, including the Milky Way. These halos contain most of a galaxy's mass and have a strong gravitational influence on the galaxy's structure. If a dark matter halo is tilted relative to a galaxy's plane, its gravitational effects could distort the galaxy over time. To figure out whether this theory is true, researchers used data from highly detailed computer simulations that modeled galactic evolution, seasoning the process with dark matter and interactions between matter and magnetic fields. The analysis revealed that the inner region of a dark matter halo can indeed tilt significantly with respect to a galaxy's plane. This tilt could result from galactic collisions or close encounters with other galaxies. Such crooked halos can stay this way for billions of years, which is long enough to warp the galactic disk. At the same time, this phenomenon isn't something unique. Astronomers have observed warped planes in other galaxies as well. In fact, nearly half of all spiral galaxies in the universe have warped disks. So, tilted dark matter halos and their gravitational effects might play a widespread role in shaping galaxies over time. While we're looking for answers, the Milky Way continues to shine brightly. But what kind of space electricity keeps its lights on? What fuels the process of star formation? After all, roughly 1 sun-sized star is born each year in the galaxy, and it needs a lot of fuel. Star formation requires hydrogen, the most abundant element in the universe. But it would still have been depleted long ago, unless there were a replenishing source. The source might be fast-moving hydrogen clouds raining down into the galaxy's disk. The hydrogen fueling the Milky Way is ionized, making it challenging to detect. Unlike atomic hydrogen, which emits light, ionized hydrogen does not. Instead, it absorbs light, which means it can only be observed when it passes in front of a bright background source. Before, astronomers used quasars, extremely bright distant space objects, as backlighting to detect these gas clouds. Unfortunately, in this case, it was impossible to determine how far away the clouds were. They could have been located anywhere between the Milky Way and the quasars billions of light years away. To pinpoint the location of the gas clouds, astronomers turned to the cosmic origin spectrograph aboard the Hubble Space Telescope. They observed 27 stars located within 10,000 light-years of the Milky Way's disk. They analyzed the stars' light and found that about half of the stars were obscured by gas clouds. It means they were close enough to directly feed the Milky Way's disk. The researchers calculated that the gas clouds contained a total mass equivalent to a whopping 110 million suns. This vast reservoir of hydrogen offers more than enough fuel to sustain the Milky Way's star formation. But where did those clouds come from? So far, it still remains a mystery. There are two main possibilities. The cloud might consist of hydrogen formed shortly after the Big Bang, primordial gas. These structures could have remained outside any galaxy for billions of years, only recently falling into the Milky Way's gravitational pull. Or the clouds might be made of material ejected from the Milky Way itself. When stars explode as supernovae, they can blow gas outward. Over time, this material could cool and fall back toward the disk, forming the clouds. We'll be able to figure out the origin of the clouds only after studying their chemical makeup. Gas from exploding stars contain heavier elements, while primordial gas created after the Big Bang is composed almost entirely of hydrogen and helium. Future ultraviolet telescopes could provide the detailed measurements needed to settle the question.